When I was a kid, I used to wonder if there were places out there that didn't belong to any star at all. Worlds with no sun to rise or set, no familiar sky, no clear sense of home. You see, most of us, including myself, grow up thinking that every planet must circle a star, tied into a system, held in place by something stable. But that assumption turns out not to be true. There are in fact planets that exist without any star at all. We call them rogue planets, worlds that drift through the galaxy unattached, following no orbit and belonging to no solar system whatsoever. They move through the darkness between stars, entirely alone, for billions of years at a time, without interruption or companion. Astronomers have confirmed that these planets really exist, and what they've discovered is surprising. Current estimates indicate that rogue planets may outnumber all the stars in the Milky Way by a factor of 20 to 1. That means for every single star you see in the night sky, there could be 20 planets wandering invisibly through space. These are not hypothetical objects or mathematical predictions. They have been directly observed using multiple detection methods over the past decade. The galaxy, it turns out, is filled with far more worlds than anyone imagined just a generation ago. I remember being genuinely fascinated the first time I learned this, and in this video, we're going to explore that same idea together, slowly and calmly. I'm glad you found your way here tonight for this particular journey through the cosmos. This video is designed for easy listening, whether you're winding down for sleep or simply resting somewhere quiet. You can follow along closely or let the words drift in the background as your mind settles. And if this kind of calm exploration helps you relax, I'd love it if you'd subscribe and let me know where you're listening from tonight. You're watching The Drowsy Astronaut. Let us begin. The first rogue planet candidates were identified in the early 2000s in a star-forming region called Sigma Orionis. These objects appeared to be planetary in mass, but showed no connection to any nearby star or stellar remnant whatsoever. They were simply there, floating freely among the young stars and gas clouds, as if they had wandered in from somewhere else. Later observations confirmed that these were not unusual flukes, but representatives of an enormous hidden population, scattered throughout the galaxy. One of the most studied rogue worlds is an object called PSOJ 3108D21. This world was discovered in 2013 using infrared surveys that could detect the faint heat signatures of objects far cooler than stars. With a mass roughly 6 to 8 times that of Jupiter, this rogue planet drifts through space approximately 80 light-years from Earth. It belongs to a group of young stars called the Beta Pictoris Moving Group, though it orbits none of them. Another fascinating example is OTS-44, a rogue world located about 550 light-years away in the constellation Chameleon. This object is particularly interesting because it sits right at the boundary between what we consider a planet and a brown dwarf. Its mass is roughly 15 times that of Jupiter, making it one of the more massive rogues discovered so far. Despite its size, it produces no significant light of its own and drifts through the void in permanent darkness. The discovery of CFBD's IR 21490403 revealed an even smaller class of rogue worlds, with masses closer to Jupiter itself. This cold, dim object was found approximately 100 light-years from Earth and appears to be only about 4 to 7 times Jupiter's mass. What makes it notable is its relatively low temperature, roughly 700 degrees Kelvin, which is cool for an astronomical object detected through infrared. It represents the kind of rogue world that may be far more common than the larger, warmer examples we have found so far. In 2021, a significant survey using data from the European Southern Observatory revealed at least 70 new rogue planet candidates in a single region of space. This region, known as the Upper Scorpius Association, is a relatively nearby stellar nursery, about 400 light-years from Earth. The sheer number of rogues found in just one area suggests that these wandering worlds are extraordinarily common throughout the galaxy. Some of the objects detected were estimated to be only 4 times the mass of Jupiter, approaching Earth-sized territory in astronomical terms. These discoveries have fundamentally changed how astronomers think about what a planet actually is and where planets can exist. For centuries, the definition of a planet was tied directly to the concept of orbiting a star, with reflected starlight making it visible. Rogue worlds challenge that definition entirely. They are planetary in size and composition, but they exist independently of any stellar system. They form a kind of shadow population, invisible to ordinary telescopes, detectable only through their faint infrared glow or gravitational effects. The masses of known rogue planets range from roughly Jupiter-sized all the way up to objects 13 times Jupiter's mass. Above that threshold, objects begin to fuse deuterium in their cores and are typically classified as brown dwarfs rather than planets. Below Jupiter's mass, rogue worlds become increasingly difficult to detect because they produce even less heat and reflect no starlight whatsoever. The smallest rogues, perhaps Earth-sized or smaller, likely exist in vast numbers but remain almost entirely invisible to current instruments. Gas giant rogues are the easiest to find because they retain significant internal heat from their formation for billions of years. This residual warmth causes them to glow faintly in infrared wavelengths, making them detectable by specialized space telescopes and ground-based observatories. Even so, finding them requires careful surveys of large regions of sky and sophisticated analysis to distinguish them from distant stars. The fact that we have found so many despite these challenges suggests the true population is enormous. Rocky rogue planets, worlds made of silicate rock and metal like Earth, are far more numerous in theory, but far harder to confirm. These smaller worlds cool much more quickly after formation and produce almost no detectable radiation in the infrared spectrum we can observe. Their presence is inferred primarily through gravitational microlensing events, brief moments when a rogue planet passes between Earth and a distant star. During these events, the rogue's gravity bends and amplifies the star's light in a characteristic way that reveals the planet's existence. Microlensing surveys have detected dozens of candidate rogue planets, including some with masses similar to Earth, or even smaller. These detections are fleeting, lasting only hours or days, and the objects can never be observed again once the alignment ends. Each detection represents a single snapshot of a world that has been drifting through space for billions of years and will continue drifting forever. The brevity of these observations makes them haunting in a way, brief glimpses of ancient wanderers passing through our field of view. Some rogue planets may have originally formed around stars and were later ejected through gravitational interactions with other planets or passing stars. Others may have formed independently, condensing directly from clouds of gas and dust, the way stars do, but without accumulating enough mass to ignite. Both pathways appear to be common, and the resulting rogue planets are essentially indistinguishable from one another once they are adrift. The galaxy makes these wandering worlds through multiple processes, all of them operating constantly across billions of years. The sheer number of rogue planets suggests they carry a significant fraction of the galaxy's total planetary mass, even if they are invisible. If estimates of 20 rogues per star are accurate, the Milky Way alone could contain several trillion wandering worlds, drifting silently through interstellar space. Most of these will never be detected by any telescope. They are simply too faint, too cold, and too far from anything luminous. They exist in the darkness, continuing their journeys whether or not any observer ever notices them. What we know about rogue planets has grown enormously in just the past 2 decades, and the picture that has emerged is one of cosmic abundance. Planets are not rare objects confined to the space around stars. They are everywhere, including the vast emptiness between stellar systems. Every region of the galaxy appears to contain them, from dense star-forming clouds to the quiet voids where almost nothing else exists. The universe, it seems, is full of worlds that wander alone. In the next part, we will explore what these rogue worlds are actually like, their surfaces, their atmospheres, and the conditions that define them. A rogue planet drifting through interstellar space exists in conditions almost impossible to imagine from the surface of Earth. There is no sunrise and no sunset, no change of seasons, no warmth from any external source reaching its surface. The only light comes from distant stars, appearing as fixed points against an unchanging black sky, with no brighter sun among them. Day and night, as concepts, simply do not exist on a rogue world. There is only an eternal, unchanging darkness. The surface temperature of a rocky rogue planet would depend almost entirely on whatever internal heat the world still retains from its formation. For a world the size of Earth that has been drifting for billions of years, that residual heat would have largely dissipated into space long ago. Surface temperatures on such a world would approach the cosmic background temperature of approximately 2.7 Kelvin, or about -450 degrees Fahrenheit. At these temperatures, even common gases like nitrogen and oxygen would freeze solid and collapse onto the surface as crystalline frost. A frozen atmosphere is one of the strangest features that might characterize an ancient rocky rogue planet without significant internal heat. The air that once surrounded the planet would gradually cool, condense, and fall like snow, eventually forming layers of frozen gas across the surface. Nitrogen frost, oxygen ice, and carbon dioxide snow would accumulate over millions of years, burying whatever terrain existed beneath. The surface would become a landscape of frozen atmosphere, eerily quiet and utterly still. For rogue planets with greater mass or more recent formation, conditions might be considerably different and somewhat less extreme overall. Larger rocky worlds retain internal heat longer because their greater volume holds more thermal energy relative to their radiating surface area. Radioactive decay in the core from elements like uranium, thorium, and potassium also continues to generate heat over billions of years. A sufficiently large, rocky rogue might maintain subsurface temperatures warm enough to keep certain materials liquid far below the frozen crust. Gas giant rogue planets present an entirely different picture, dominated by thick atmospheres and surprising internal warmth that persists across cosmic timescales. Jupiter, in our own solar system, radiates nearly twice as much heat as it receives from the Sun due to ongoing contraction and cooling. A Jupiter-sized rogue planet would continue this process indefinitely, glowing faintly in infrared even without any stellar input to supplement its energy budget. These warm gas giants would be the most detectable rogues and perhaps the most dynamic, with active weather systems driven by internal heat. The atmosphere of a rogue gas giant would likely contain the same basic components found in Jupiter and Saturn: hydrogen, helium, and traces of other molecules. Ammonia clouds, methane haze, and water vapor could all exist at various depths within the layered atmosphere of such a world. Storms might develop and persist for centuries, driven by the temperature differences between the warm interior and the cold outer layers exposed to space. Lightning could flash in the depths of these storms, illuminating cloud banks that no external light ever reaches. Cloud structures on a rogue gas giant would form in layers, with different compounds condensing at different altitudes, depending on temperature gradients. Deep in the atmosphere, where temperatures might exceed 1000 degrees Kelvin, there would be no clouds at all, just hot, dense gas. Higher up, water vapor would condense into clouds of liquid water droplets or ice crystals, similar to Earth's own cloud formations. Even higher still, ammonia and ammonium hydrosulfide would freeze into layers of brownish or reddish haze. The colors of a rogue gas giant would be muted compared to the vivid bands we see on Jupiter, simply because there is no sunlight to illuminate them. Any visible coloration would come from faint thermal glow radiating up from the warmer interior through the semi-transparent upper atmosphere. In infrared vision, these worlds would appear as warm orbs against the cold background of space, their banded structures visible as variations in emitted heat. They would be invisible to the naked eye, but strikingly present to instruments designed to detect thermal radiation. Smaller rogue worlds, those closer in mass to Neptune or Uranus, would occupy an intermediate category between rocky planets and gas giants. These ice giant rogues would have thick atmospheres of hydrogen and helium, surrounding mantles of water, ammonia, and methane, in compressed, exotic forms. They would retain heat more effectively than rocky worlds, but less effectively than the largest gas giants, placing their temperatures somewhere in between. Many of these intermediate rogues likely exist, though they are harder to detect than either the largest or smallest examples. The moons of rogue gas giants, if any survived the ejection process that sent the planet wandering, would exist in fascinating conditions. Tidal heating from the gravitational interaction between the rogue planet and its moons could generate warmth independent of any stellar source whatsoever. In our own solar system, Jupiter's moon Europa maintains a subsurface ocean through exactly this mechanism, kept liquid by gravitational flexing. A rogue gas giant's moon might sustain similar conditions indefinitely, warmed by tides even in the darkest reaches of interstellar space. The magnetic fields of rogue gas giants would likely persist for billions of years, generated by the convection of metallic hydrogen deep in their interiors. These magnetic fields would interact with the sparse particles of the interstellar medium, creating faint auroras at the planet's poles. Unlike the auroras on Jupiter, which are powered partly by the solar wind, rogue planet auroras would be solely products of internal dynamics. They would glow faintly in the darkness, unseen by any observer, flickering over landscapes that no telescope has ever resolved. Rocky rogue planets might also retain magnetic fields if their iron cores remained molten and convective, though this would depend on size and thermal history. A Mars-sized rogue would likely have lost its magnetic field early in its history, just as Mars itself did within its first billion years. An Earth-sized or larger rocky rogue might maintain a dynamo for much longer, protecting any remaining atmosphere from erosion by cosmic rays. The presence of such a field would be essentially undetectable from Earth's distance, but it would shape the environment of the rogue profoundly. The surface features of a rocky rogue planet would be frozen in time in ways that surfaces on star-orbiting worlds are not. Without atmospheric weathering from wind or rain, without tectonic activity driven by mantle convection, and without temperature cycles, the surface would change almost imperceptibly. Impact craters from ancient collisions would remain pristine for billions of years, their rims sharp and their floors unaltered by erosion. Mountains and valleys from the planet's early geological history would stand unchanged, monuments to processes that ended long before the planet began its wandering. Some rogue planets may have formed with thick hydrogen-helium envelopes that they retained even at relatively small sizes, creating unusual atmospheric conditions. A rocky core surrounded by a dense primordial atmosphere could trap heat far more effectively than a bare rocky surface would allow. These shrouded rogues might maintain surprisingly warm surface temperatures, perhaps even warm enough for liquid water under the right pressure conditions. The possibility of such worlds has led some researchers to speculate about habitability on rogue planets, a topic we will explore later. The diversity of rogue worlds likely mirrors the diversity of planets. Found orbiting stars, spanning every size and composition that planetary formation can produce. Some may be iron-rich remnants of shattered larger bodies. Others may be icy worlds from the outer reaches of lost solar systems, now adrift forever. Still others may be entirely novel, formed under conditions that do not occur in any known planetary system today. Each rogue is a unique outcome of complex processes, carrying its history through the galaxy in frozen form. Now, we will explore how these wandering worlds come to exist, whether cast out from planetary systems or born alone. Rogue planets arise through two distinct pathways, each producing wandering worlds that are ultimately indistinguishable once they are adrift between the stars. The first pathway is ejection, planets that originally formed in orbit around a star but were flung outward by gravitational chaos. The second pathway is direct formation, planets that condensed independently from gas clouds, like stars, but never accumulated enough mass to ignite nuclear fusion. Both processes appear to be common, and both contribute to the enormous population of rogues scattered throughout the galaxy. Planetary ejection happens during the violent early phases of solar system formation, when multiple planets are still jostling for stable orbits around their star. Young planetary systems are crowded places, with protoplanets growing rapidly and gravitationally influencing each other's paths in complex ways. When two massive planets pass close to each other, the gravitational interaction can dramatically alter both of their orbits in a single encounter. In some cases, one planet gains energy and moves to a more distant orbit, while the other loses energy and spirals inward. If the energy transfer is strong enough, the outward moving planet may exceed the escape velocity of the entire stellar system and leave forever. This ejection process is not gentle. The planet is essentially thrown out of its home system at high speed, never to return again. Once free of the star's gravitational pull, the planet continues moving through interstellar space at whatever velocity it carried during the ejection event. These ejected worlds become rogues, not by choice but by circumstance, exiles from systems that could not accommodate all their members. Computer simulations of early solar system dynamics consistently show that ejection events are common, perhaps even inevitable in most planetary systems. Systems that begin with multiple gas giants frequently end with fewer, the missing planets having been scattered outward into the void during the settling process. The planets that remain achieve stable, well-separated orbits only because the unstable members were removed through this gravitational selection mechanism. Ejection is not a failure of planetary formation. It is a natural byproduct of the process working as it normally does. Our own solar system may have experienced such ejection events in its distant past, losing one or more planets to the interstellar void. Some models suggest that a fifth giant planet once existed in the outer solar system, orbiting beyond Neptune in the early configuration. Gravitational interactions with Jupiter may have eventually flung this hypothetical planet outward, where it became a rogue wandering somewhere in the galaxy. If this scenario is accurate, there may be a world that formed alongside Earth and now drifts alone, billions of miles from any star. The ejection of smaller planets, rocky worlds like Earth or Mars, would be even more common than the ejection of giants. Smaller planets are more easily perturbed by the gravitational influence of larger neighbors, making them vulnerable to displacement during unstable phases. A single close encounter with a Jupiter-mass planet could send an Earth-mass world sailing out of its system entirely, carrying whatever atmosphere and water it possessed. The galaxy may be filled with Earth-sized rogues that once orbited stars, perhaps even stars similar to our own Sun. The second formation pathway, direct collapse from gas clouds, produces rogues that were never part of any stellar system at all. These planets form in the same molecular clouds where stars are born, condensing from dense pockets of gas and dust that contract under their own gravity. Unlike protostars, these objects never accumulate enough mass to initiate hydrogen fusion and ignite as true stars, or even brown dwarfs. They simply become planetary mass objects, glowing faintly from the heat of their contraction, then cooling slowly as they drift away. The boundary between a directly formed rogue planet and a very low-mass brown dwarf is not entirely clear and remains a subject of ongoing study. Traditionally, the dividing line has been set at roughly 13 Jupiter masses, the threshold above which deuterium fusion can briefly occur in the core. Objects below this threshold are considered planets, while those above are brown dwarfs, though both types can form through the same process. Some astronomers prefer to classify directly formed objects as a separate category entirely, regardless of their mass. Direct formation appears to be responsible for many of the rogue planets found in young star-forming regions, where the process can be observed in action. In regions like the Upper Scorpius Association, dozens of planetary mass objects have been detected drifting freely among the newly formed stars nearby. These objects are too young to have been ejected from planetary systems. They formed in place as the cloud fragmented into pieces both large and small. Their presence confirms that planetary mass objects can arise independently of any star, challenging older assumptions about how planets must come to exist. The relative contribution of each pathway to the total rogue population is still uncertain, and estimates vary depending on modeling assumptions and observational data. Some studies suggest that ejection is the dominant source, producing perhaps 10 rogues for every star through chaotic scattering alone across the galaxy. Other analyses emphasize direct formation, noting that the smallest cloud fragments could produce planetary mass objects in enormous numbers during each star formation episode. The true answer likely involves both processes operating together, each contributing significantly, to the wandering population. One way to distinguish between ejected rogues and directly formed rogues might be through their velocity distributions within the galaxy, though this is difficult to observe. Ejected planets would carry the velocity signatures of their host star systems plus the additional kick imparted during their expulsion from that system. Directly formed rogues would move with velocities characteristic of the clouds in which they formed, without any additional ejection component present. In practice, these signatures are subtle and have not yet been conclusively detected, leaving the origin of most individual rogues uncertain. The composition of a rogue planet might also hint at its formation history, though observing composition in such faint objects is extremely challenging. An ejected rocky planet would likely contain the same materials found in rocky planets orbiting stars: silicates, iron, and volatile compounds from the inner regions. A directly formed gas-dominated rogue would more closely resemble a miniature star in composition, with roughly solar proportions of hydrogen, helium, and heavier elements throughout. These compositional differences remain largely theoretical for now, awaiting future instruments capable of detailed spectroscopy of faint, cold objects. Regardless of how they form, rogue planets share the same ultimate fate: eternal wandering through the vast emptiness between the stars of the galaxy. An ejected planet and a directly formed planet of similar mass would be essentially identical after a few billion years of cooling and drifting through space. Both would occupy the same temperature ranges, display the same faint infrared signatures, and respond to the same gravitational influences from passing stars. The galaxy does not distinguish between them. They are simply rogues, part of the invisible majority that populates interstellar space. The recognition that planets can form through multiple pathways has broadened our understanding of what planets are and where they can exist. Planets are not merely accessories to stars. They are a natural outcome of cosmic processes that operate independently of stellar formation in many cases. The universe produces planets abundantly, scattering them throughout space regardless of whether a convenient star is available for them to orbit. Rogue worlds are not anomalies. They are a fundamental component of galactic structure, as common as the stars themselves. Now, we will look more closely at the ejection process, exploring how our own solar system may have lost worlds to the void. The process by which planets are thrown out of their home systems is one of the most dramatic phenomena in celestial mechanics, even though it happens in silence. Gravitational interactions between planets can build up over millions of years, gradually nudging orbits into unstable configurations that eventually collapse in spectacular fashion. When instability finally triggers, the results can unfold over mere thousands of years. A blink of an eye in cosmic terms, but an eternity in human experience. Entire worlds are redirected, scattered inward toward their star, or outward into the endless dark between solar systems. The physics behind planetary ejection is relatively straightforward, governed by the same gravitational laws that keep planets in stable orbits under normal circumstances. When two massive planets pass within a certain critical distance of each other, they exchange orbital energy through their mutual gravitational attraction in significant amounts. One planet typically gains energy, which translates into a larger, more elongated orbit extending further from the star it originally circled. The other planet loses energy, causing its orbit to shrink and potentially bringing it closer to other planets or even the star itself. If the energy transfer is sufficiently extreme, the outward moving planet can reach escape velocity and leave the system entirely, never to return again. Escape velocity depends on the mass of the central star and the distance from which the planet is escaping. But for our solar system, it is only about 4 kilometers per second at Neptune's distance. A single close encounter with Jupiter can easily impart this much additional velocity to a smaller planet, more than enough to unbind it from the Sun's gravity. The ejected planet then continues on a hyperbolic trajectory, curving away from the system and eventually straightening into a nearly linear path through interstellar space. Computer models of early planetary system formation routinely produce ejection events, often multiple ejections from a single system over its chaotic early history. These simulations begin with protoplanetary disks containing more mass than the final stable configuration can accommodate in long-term balanced arrangements. As planets grow and migrate through the disk, they inevitably encounter orbital resonances and close approaches that destabilize their arrangement eventually. The excess planets are removed through ejection, leaving behind only those that happen to find stable, widely separated orbits after the chaos subsides. Our own solar system shows signs of having undergone significant orbital rearrangement early in its history, suggesting that ejection events may have occurred here. The Nice model, named after the French city where it was developed, proposes that the outer planets originally formed in a more compact configuration. Gravitational interactions, possibly triggered by the planets crossing orbital resonances, caused a period of instability about 4 billion years ago that is recorded in history. During this upheaval, Uranus and Neptune may have swapped positions and both migrated outward to their current distant orbits from closer to the Sun. Some versions of the Nice model include a fifth giant planet, roughly Neptune mass, that was present in the early solar system but did not survive the instability. In these simulations, gravitational encounters with Jupiter and Saturn eventually eject this hypothetical planet from the solar system entirely, sending it into interstellar space forever. The remaining 4 giant planets then settle into their current orbits, with the expelled fifth member becoming a rogue world wandering somewhere in the galaxy today. If accurate, this means one of our own planetary siblings drifts alone in the darkness, forever separated from its birthplace around our Sun. The evidence for a missing fifth giant is indirect but intriguing, based on how well the model explains other features of the solar system. The current orbital architecture of the outer planets, the structure of the Kuiper Belt, and the late heavy bombardment of the inner solar system can all be explained more naturally when a fifth giant planet is included in simulations. Without the fifth planet, some of these features are harder to reproduce, requiring more finely tuned initial conditions that seem less likely to arise naturally. The ejection hypothesis remains unproven, but is taken seriously by many planetary scientists studying our system's history. Smaller planets are even more vulnerable to ejection than giants because they are more easily accelerated by gravitational encounters with more massive bodies. An Earth-mass planet passing too close to Jupiter would gain far more velocity per unit mass than Jupiter would lose, making escape almost inevitable. This asymmetry means that terrestrial planets in the inner solar system could be scattered outward by migrating giants, lost forever to interstellar space. Mars-sized or even Earth-sized rogues may be extremely common in the galaxy as a result of this process operating in countless young systems. The timing of ejection events varies from system to system, depending on the specific orbital configuration and the masses of the planets involved. Some systems may eject planets within their first few million years, during the chaotic gas-rich phase of disk evolution, when migration is rapid. Others may remain marginally stable for billions of years before a slow drift into resonance finally triggers instability and ejection in a delayed fashion. Still others may retain all their planets indefinitely, never experiencing the close encounters that would lead to scattering events at all. Once ejected, a planet carries not only momentum, but also whatever physical characteristics it possessed at the moment of expulsion from its original system. A rocky planet with an atmosphere would retain that atmosphere, at least initially, as it departed into the cold of interstellar space alone. Moons orbiting the planet at the time of ejection might remain gravitationally bound, accompanying their parent world on its wandering journey forever. The ejected system, planet, moons, and perhaps rings, would persist as a miniature solar system without a sun, drifting through the galaxy intact. The speed of an ejected planet relative to the galaxy depends on both the ejection velocity and the motion of its original star through the galactic disk. Most ejected planets would move at speeds of a few kilometers per second relative to nearby stars, similar to the velocity dispersion of stars themselves. Some, ejected from particularly energetic encounters, might move considerably faster, eventually traveling great distances from their birth region over billions of years. A rogue planet born near the galactic center could drift outward into the galactic halo over cosmic timescales, or vice versa. The realization that ejection is common has implications for understanding the architecture of observed exoplanetary systems around other stars beyond our solar system. Many known exoplanet systems appear remarkably compact, with multiple planets orbiting closer to their star than Mercury orbits our Sun in tight arrangements. These compact configurations may represent systems that avoided ejection, retaining all their planets because they never experienced strong gravitational scattering during formation. Alternatively, they may be the stable survivors of systems that once contained additional members, now departed and wandering as rogues. Ejection events have likely been occurring throughout the galaxy's entire history, continuously replenishing the population of rogue worlds over billions of years. Every generation of star formation produces new planetary systems, and a significant fraction of those systems eject one or more planets during their settling phase. The rogues accumulate over time, their numbers growing even as individual rogues disperse through the galaxy and become harder to detect with each passing era. The population we observe today represents the integrated output of ejection processes operating since the Milky Way's earliest epochs of active star formation. In the next part, we will explore how astronomers estimate the true number of rogue planets hiding in the darkness between the stars. Estimating the population of rogue planets presents a unique challenge because these worlds produce almost no light of their own and reflect nothing. Unlike planets orbiting stars, which can be detected through the starlight they block or reflect, rogues are isolated points of faintness against empty space. The only signals they produce are their own feeble infrared glow from residual heat and the gravitational effects they exert on light passing nearby. Astronomers have developed clever techniques to exploit both of these signatures, gradually building a census of the invisible population that surrounds us. Infrared surveys can detect the warmest and most massive rogue planets, those that still glow faintly from the heat of their formation. Young rogues, less than a few 100 million years old, retain enough thermal energy to stand out against the cold background of space in infrared observations. The WISE spacecraft, which surveyed the entire sky in infrared wavelengths, detected numerous brown dwarf candidates and possible rogue planets during its mission lifetime. Ground-based observatories with adaptive optics have followed up on these detections, confirming the nature of many candidate objects as genuine free-floating planetary mass bodies. The limitation of infrared detection is that only the youngest, warmest rogues are visible to our current instruments designed for this purpose. Older rogues that have cooled for billions of years fall below the detection threshold, disappearing into the background noise of the observations entirely. Since most rogue planets are presumably old, formed early in the galaxy's history and cooling ever since, the infrared detected population represents only a small fraction. The true number of rogues is almost certainly much higher than what infrared surveys alone can reveal to observers. Gravitational microlensing offers a complementary approach that can detect rogues of any temperature, including those that produce no detectable light whatsoever. When a rogue planet passes directly between Earth and a distant background star, its gravity bends and magnifies the star's light in a predictable way. The magnification event typically lasts only hours or days, depending on the mass of the lensing object and the geometry of the alignment involved. By monitoring millions of stars and watching for these brief, brightening events, astronomers can detect rogues that would otherwise be completely invisible to all instruments. Several major microlensing surveys have operated over the past 2 decades, accumulating thousands of candidate events that reveal dark objects in the foreground of observed regions. The OGLE project, operating from Chile, has monitored the galactic bulge for microlensing events since the 1990s, with remarkable consistency. The MOA collaboration in New Zealand has conducted similar observations, providing overlapping coverage that improves detection reliability and statistical confidence in results. Together, these surveys have identified dozens of events consistent with rogue planets, including some with masses similar to Earth or even smaller than Earth. The statistics from microlensing surveys suggest that rogue planets are extraordinarily common, numbering in the billions or even trillions across the entire Milky Way galaxy. Early estimates, based on limited data, suggested roughly 2 rogues for every star in the galaxy, already a surprisingly large number by historical standards. More recent analyses, incorporating larger datasets and refined models of planetary ejection, have pushed estimates even higher than those initial calculations indicated. Some studies now suggest that rogues outnumber stars by a factor of 10, 20, or even more, depending on assumptions about the low-mass end of the distribution. The mass distribution of rogue planets is a critical unknown that profoundly affects population estimates derived from all available observational data. If rogue planets follow a distribution similar to planets orbiting stars with many more small worlds than large ones, then the total number could be enormous. Earth mass and smaller rogues would dominate the population, vastly outnumbering the Jupiter-mass giants that are easier to detect through either infrared or microlensing methods. Unfortunately, the smallest rogues produce the shortest, weakest microlensing events, making them the hardest to detect and count accurately with current observational capabilities. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the mid-20s, will dramatically improve our ability to detect and characterize rogue planets through microlensing. From its position in space, Roman will monitor the galactic bulge with unprecedented precision, catching brief microlensing events that ground-based telescopes would miss entirely. The mission is expected to detect hundreds of rogue planet candidates, including many with masses down to Mars size or below the mass of Mars itself. This dataset will allow astronomers to constrain the mass distribution of rogues for the first time with real statistical confidence. The spatial distribution of rogue planets throughout the galaxy is another important question that observations are beginning to address through careful survey design. Rogues should be concentrated in the galactic disk and bulge, where most star formation has occurred and most ejection events have taken place over cosmic history. The density of rogues likely increases towards the galactic center, mirroring the stellar density and the rate of planetary system formation in that region. Relatively few rogues would be expected in the galactic halo, though some may have been scattered there through extreme ejection events or galactic dynamical processes. If current estimates are accurate, a rogue planet may pass through our solar system's outer reaches every few tens of thousands of years on average. The chance of a close approach within the orbit of Neptune, say, is much lower, occurring perhaps once every 10 million years or so statistically. These passages would be completely invisible to us unless the rogue happened to pass close enough to perturb the orbits of known objects detectably. The nearest rogue planet to Earth at any given moment is probably tens of light years away, too distant to observe directly, but close enough to contemplate. The realization that rogues may constitute the galaxy's most numerous class of planetary objects has profound implications for how we think about planets as a phenomenon. Planets are not primarily objects that orbit stars. They are objects that sometimes orbit stars, but often do not orbit anything at all. The galaxy's planetary mass may be distributed more broadly than its stellar mass, scattered through interstellar space, as well as concentrated in systems around observable stars. We live in a galaxy of wanderers, and our own solar system is an island of gravitational order in a sea of drifting, unbound worlds. Counting what we cannot see requires inference, modeling, and careful statistical analysis, applied to the limited observational data we can gather from our vantage point. Every estimate of the rogue population carries significant uncertainty, reflecting our incomplete understanding of formation and ejection rates across galactic history. What seems clear is that the number is large, not thousands or millions, but billions or trillions of wandering worlds filling the spaces between stars. The galaxy is far more crowded than visible light reveals, populated by dark planets that far outnumber the bright stars we can easily observe. Now let us return to the rogue planets themselves, exploring the lonely giants, the massive gas worlds that retain their warmth across cosmic time. Among all the rogue worlds drifting through the galaxy, the gas giants are perhaps the most remarkable because they carry their own warmth with them. These massive planets, similar in size to Jupiter or larger, retain significant internal heat for billions of years after their formation originally occurred. This heat comes from several sources: the slow gravitational contraction of the planet itself, residual thermal energy from the planet's formation, and radioactive decay occurring within their deep interiors. Unlike rocky rogues that cool to the ambient temperature of space, gas giant rogues remain warm islands in the cold darkness between all stars. Jupiter, in our own solar system, provides a useful model for understanding how rogue gas giants might behave in the absence of any stellar illumination. Our Jupiter radiates nearly twice as much energy as it receives from the Sun, meaning most of its thermal output is internally generated rather than solar in origin. This internal heat drives Jupiter's complex weather patterns, powering the jet streams and storms that characterize its banded appearance visible to observers. A rogue Jupiter, receiving no solar energy at all, would continue these same processes, powered entirely by its own internal heat sources, indefinitely. The atmospheric dynamics of a rogue gas giant would differ somewhat from Jupiter's, primarily because the temperature difference between day and night sides would not exist. On Jupiter, the side facing the Sun is slightly warmer than the night side, creating subtle circulation patterns that influence weather at regional scales. A rogue would experience no such asymmetry. Its atmosphere would be heated uniformly from below, creating purely convection-driven weather patterns throughout the entire atmosphere. The result might be more symmetric storm systems, with jet streams driven by the planet's rotation and internal heat alone, rather than any external forcing. The Great Red Spot on Jupiter is an anticyclonic storm that has persisted for at least 400 years, and possibly much longer than human records can confirm. A rogue gas giant could sustain similar long-lived storms, perhaps for even longer periods, given the absence of any external perturbations from varying solar input. These storms would churn endlessly in the darkness, their clouds swirling in patterns no telescope has ever resolved, and perhaps never will resolve. The energy driving them would come from the deep interior, welling up through the atmosphere in invisible convective plumes that transport heat outward. Lightning would likely occur within the storm clouds of a rogue gas giant, just as it occurs within Jupiter's atmosphere based on observations. Jovian lightning has been directly observed by spacecraft, illuminating cloud tops with flashes visible from orbit during atmospheric electrical discharge events. On a rogue world, lightning would be one of the few sources of visible light, brief flashes in an otherwise completely dark sky. These electrical discharges would occur at depths where water clouds form, similar to thunderstorms on Earth, but vastly larger in scale and energy. The interior structure of a rogue gas giant would resemble that of any other gas giant, with layers of increasing pressure and density extending down toward the core. Beneath the visible cloud tops, hydrogen gas gradually transitions into liquid hydrogen as pressure increases with depth over thousands of kilometers. Deeper still, at pressures exceeding millions of atmospheres, hydrogen becomes metallic, a bizarre state where electrons move freely, conducting electricity like a metal. This metallic hydrogen region generates the planet's powerful magnetic field through convective dynamo processes, just as iron in Earth's core generates our own magnetic field. The magnetic field of a rogue gas giant would extend far into space, creating a magnetosphere that interacts with the sparse particles of the interstellar medium constantly. This interaction would produce faint auroras at the planet's magnetic poles, where charged particles from interstellar space funnel inward along field lines toward the atmosphere. Unlike auroras on Jupiter, which are partly powered by particles from the Sun and volcanic emissions from Io, rogue planet auroras would rely entirely on interstellar material. They would glow faintly in ultraviolet and infrared, invisible to human eyes, but real nonetheless above the cloud tops. If a rogue gas giant retained moons during its ejection from a stellar system, those moons might experience fascinating conditions driven by tidal heating mechanisms. Tidal heating occurs when the gravitational pull of a massive planet flexes the interior of an orbiting moon, generating friction and heat internally. Jupiter's moon Io is the most volcanically active body in our solar system because of this process, constantly squeezed and stretched by Jupiter's gravity. A moon orbiting a rogue gas giant could experience similar heating, maintaining geological activity and potentially liquid water despite the absence of any nearby star. Europa, another of Jupiter's moons, almost certainly harbors a global ocean of liquid water beneath its icy surface, kept liquid by tidal heating from Jupiter. A Europa-like moon orbiting a rogue gas giant could maintain similar conditions indefinitely, its ocean insulated from the cold of space by kilometers of ice. These subsurface environments would be completely isolated from the external universe, dark and silent, but potentially chemically active at their floors. If life can exist on Europa, and many scientists believe it might, then life could also exist on moons of rogue gas giants drifting through interstellar space. The cloud composition of a rogue gas giant would vary with depth, forming distinct layers visible as bands and zones in infrared imaging observations. The outermost layers, exposed to the cold of space, would consist of ammonia ice crystals forming white or yellowish clouds at high altitudes. Deeper down, ammonium hydrosulfide would condense into brownish clouds, while water, ice, and liquid water clouds would form at greater depths still. The deepest visible clouds, in the warm regions where temperatures might exceed room temperature, could contain exotic compounds not found in any environment on Earth. The color of a rogue gas giant, if any observer could see it, would depend on the chemical composition of its cloud tops and any chromophore compounds present. Jupiter's distinctive reddish-brown bands are caused by complex organic molecules and possibly sulfur compounds elevated from deeper atmospheric layers upward. A rogue gas giant might display similar coloration, though without sunlight to illuminate these clouds, they would only be visible through their own faint thermal glow. In infrared, the planet would appear as a warm disk against the cold background, with darker and lighter bands indicating regions of different temperature. The lifetime of a rogue gas giant's internal heat is measured in billions of years, long enough for these worlds to remain warm across most of cosmic history. A Jupiter mass rogue formed early in the galaxy's history, 10 billion years ago, would still retain significant internal heat today from its formation. Even after all this time, it would glow in infrared at temperatures of perhaps 100 to 200 Kelvin, noticeably warmer than the cosmic background. These ancient rogues would be among the oldest coherent structures in the galaxy, predating most of the stars currently shining around them. In the next part, we will explore the smaller rogues, rocky and icy worlds that wander without the warmth of a giant's internal furnace. For every massive gas giant drifting through the galaxy, there are likely many more smaller rogues, worlds of rock and ice that wander in silence and cold. These rocky drifters are far harder to detect than their giant cousins because they produce almost no infrared glow after their first few 100 million years. An Earth-sized rogue that formed 8 billion years ago would now be indistinguishable from the empty space around it to nearly all of our instruments. Only through gravitational microlensing can we hope to detect these small, cold worlds, and even then, only when they happen to pass before a distant star. The surfaces of ancient rocky rogues would be among the coldest places in the universe, approaching the temperature of the cosmic microwave background itself. At roughly 3 degrees above absolute zero, any atmosphere the planet once possessed would have long since frozen and fallen as snow onto the surface. Nitrogen, oxygen, carbon dioxide, and even noble gases like argon would exist as crystalline deposits layered across the landscape in frozen sheets and drifts. The surface would be entombed in its own former atmosphere, buried under ice that was once breathable air. Whatever geological features the planet possessed at the time of its ejection would remain essentially unchanged for billions of years afterward. Mountain ranges raised by ancient tectonic forces would stand exactly as they stood when the last internal heat faded and the planet's crust stiffened into permanent stillness. Impact craters from the bombardment era would preserve their sharp rims and central peaks, unweathered and uneroded across vast stretches of cosmic time. The surface would be a museum of the planet's early history, frozen in time at the moment when geological activity ceased forever. If the rogue planet possessed oceans at the time of its ejection, those oceans would have frozen as the planet cooled, forming a global ice cap. The freezing process would have begun at the surface and worked downward, with the ice layer thickening over millions of years gradually. Eventually, even the deepest waters would solidify, unless the planet retained enough internal heat to maintain liquid pockets somewhere in its deep interior. The frozen ocean would record the planet's last moments of warmth, its ice preserving whatever chemistry and perhaps biology existed before the cold arrived. Rocky rogues that formed with substantial hydrogen-helium atmospheres might maintain more habitable conditions than their bare surface counterparts across cosmic timescales. A thick primordial atmosphere could trap heat from the planet's interior, creating a greenhouse effect that keeps surface temperatures elevated significantly above cosmic background levels. Even without internal radioactive heating, the pressure of a dense atmosphere can raise the effective temperature through adiabatic compression effects. Such a world might maintain liquid water on its surface indefinitely, warmed not by a star but by its own atmospheric blanket. The possibility of liquid water on rogue planets has led some researchers to speculate about the habitability of these dark, isolated worlds adrift between stars. Water is essential for life as we understand it, and the presence of long-lived liquid water environments would satisfy at least one requirement for habitability. Energy sources would also be needed, but these might come from geothermal vents on the ocean floor or from chemical reactions in the planet's crust. The conditions for life, however minimal, might exist on some rogue planets, even in the absence of any stellar input whatsoever. Ice giant rogues, worlds similar to Uranus and Neptune, would occupy a middle ground between rocky drifters and gas giants in several respects. These planets possess thick atmospheres of hydrogen and helium, but their interiors are dominated by water, ammonia, and methane in compressed exotic forms. They would retain internal heat longer than rocky worlds, but less effectively than the largest gas giants, placing them in an intermediate temperature range. Many such worlds probably exist as rogues, ejected from the outer reaches of planetary systems where ice giants commonly form around other stars. The moons of ejected ice giants might maintain subsurface oceans through tidal heating, similar to the moons of rogue gas giants described earlier in this series. A Triton-like moon orbiting a rogue Neptune could experience enough tidal flexing to keep its interior warm and its water ice melted at depth. These moons would be completely isolated from any external energy source, dark and silent but potentially hostile to simple life forms nonetheless. The universe may contain countless such worlds, warmed not by stars but by the gentle gravitational kneading of their host planets over billions of years. Smaller rogues, Mars-sized or smaller, would cool rapidly and possess virtually no internal heat after their first few 100 million years of existence. These tiny wanderers would be the most numerous of all rogues, if the mass distribution follows patterns similar to planets orbiting stars currently. Detecting them is extremely difficult because they produce no infrared signature and create only brief, weak microlensing events when they pass before background stars. They might outnumber all other rogues combined, yet remain almost entirely invisible to our surveys and observational programs for the foreseeable future. Some of the smallest rogues might be fragments of larger worlds, shattered by ancient collisions and scattered into the void as independent bodies. These fragments could range from moon-sized objects down to asteroid-scale chunks, depending on the violence of the collision that created them in past epochs. Whether such fragments qualify as rogue planets is partly a matter of definition, but they would certainly share the same fate of eternal wandering. The interstellar medium may contain a continuum of rocky debris, from planet-sized rogues down to individual boulders tumbling through the darkness. The discovery of Oumuamua in 2017 provided our first confirmed observation of an interstellar object passing through our solar system from elsewhere. This elongated object, perhaps 200 meters long, likely originated as debris from another star system, possibly from a rogue planetary body somewhere in the galaxy. Its passage reminded astronomers that the space between stars is not truly empty. It is filled with objects of all sizes, occasionally passing through our cosmic neighborhood. Oumuamua was too small to be called a planet, but it represented the small end of a continuum that extends up to Earth-sized worlds and beyond. Rocky rogues carry the histories of their origin systems with them as they drift through the galaxy. Frozen records of distant planetary formation processes. An Earth-like rogue might have the same bulk composition as our own planet, formed in the habitable zone of a sun-like star before being ejected. Its frozen surface might preserve evidence of past volcanic activity, ancient oceans, and perhaps even biological processes that flourished before the ejection cut off stellar warmth. These worlds are time capsules, preserving planetary conditions from billions of years ago in unchanging frozen form. In the next part, we will explore the fascinating question of whether life could exist on rogue planets, worlds without any starlight to power their biospheres. The question of whether rogue planets could support life is one of the most intriguing puzzles in astrobiology, challenging our assumptions about what life requires. For most of human history, sunlight was considered essential for life. Plants use it for photosynthesis, which forms the base of Earth's food chains entirely. The discovery of deep-sea hydrothermal vents in the 1970s revealed that complex ecosystems can thrive in total darkness, sustained by chemical energy rather than light. This discovery fundamentally changed how scientists think about life in the universe and opened new possibilities for life on starless worlds. At hydrothermal vents on Earth's ocean floor, superheated water emerges from cracks in the crust, carrying dissolved minerals and chemicals from below the sea floor. Bacteria living near these vents extract energy from chemical reactions, particularly the oxidation of hydrogen sulfide and other compounds rising from volcanic sources. These chemosynthetic bacteria form the base of local food webs, supporting diverse communities of worms, crustaceans, fish, and other organisms in complete darkness. No sunlight reaches these ecosystems, and none is needed. The energy comes entirely from Earth's internal geological processes continuing beneath the surface. If hydrothermal ecosystems can exist on Earth without sunlight, they could potentially exist on rogue planets with sufficient internal heat as well. A rogue world with a liquid subsurface ocean kept warm by radioactive decay or tidal heating might host hydrothermal vents on its ocean floor. These vents could provide the same chemical energy sources that power vent ecosystems on Earth, supporting similar metabolic processes in alien organisms. The life forms in such an ocean would never see a star, never experience daylight, and never know that anything existed beyond their dark, warm waters. The requirements for such life would be liquid water, chemical energy sources, and the right molecular building blocks dissolved in the ocean environment. Water is common throughout the galaxy, and rogue planets that formed in the water-rich outer regions of planetary systems might carry substantial ice layers. Chemical energy could come from serpentinization reactions, where water interacts with iron-rich rocks to produce hydrogen, or from volcanic activity on the ocean floor. The necessary building blocks, carbon, nitrogen, phosphorus, sulfur, would likely be present if the planet formed from typical interstellar material. One limiting factor for life on rogue planets might be the formation of life in the first place, which may require conditions that only exist around stars. On Earth, the complex organic molecules that eventually gave rise to life may have formed through reactions driven by ultraviolet light from the young sun. Without a star, a rogue planet might lack the energy sources needed to synthesize these precursor molecules from simpler ingredients in the first place. This suggests that life on a rogue might need to originate elsewhere, perhaps when the planet still orbited a star, before surviving the transition to interstellar wandering. A rogue planet ejected from a planetary system after life had already arisen might carry that life with it into the void indefinitely. If the planet possessed a subsurface ocean protected by an ice shell, the life in that ocean might never notice the ejection event at all. The surface would freeze, the atmosphere would collapse, but deep below the ice, life could continue as before, sustained by heat from the interior. Billions of years later, that life might still persist, completely isolated from the rest of the universe, evolving in directions determined only by its own internal dynamics. The evolution of life on an isolated rogue planet would follow entirely different trajectories than life on worlds with surface environments exposed to space. There would be no seasons to adapt to, no weather changes, no variations in energy input from any external source, like a star. The environment would be stable across billions of years, changing only as the planet's internal heat gradually diminished over cosmic timescales and processes. Life in such a setting might evolve very slowly, with little selective pressure driving adaptation once organisms became well suited to their unchanging environment. Intelligence, if it could arise in such an environment, would face unique philosophical challenges unknown to surface-dwelling civilizations like our own. Beings in a subsurface ocean would have no concept of stars, planets, or the astronomical universe that exists beyond their ice ceiling above them. Their entire cosmos would be the ocean, the rocky floor, and the ice above. They might not even recognize that anything else existed to explore. The question of whether other life exists elsewhere would be meaningless to them, since they would have no framework for imagining elsewhere at all. The number of rogue planets that might harbor life is entirely unknown, but even a small fraction of 1 trillion rogues would represent an enormous number of potential biospheres. If 1 in a million rogues possesses conditions suitable for life, and even a fraction of those actually develop life, the galaxy might contain millions of isolated biospheres. These islands of life would drift through the galaxy, each one completely unaware of the others, each evolving independently for billions of years. The universe might be full of life that we will never detect because it exists in environments completely inaccessible to our observations from any distance. The concept of panspermia, life spreading between worlds through natural processes, takes on interesting dimensions when rogue planets are considered as potential carriers. A rogue planet passing through a stellar system might exchange material with planets there, potentially transferring microorganisms between totally unrelated star systems. Alternatively, a life-bearing rogue might be captured by a new star, delivering its cargo of organisms to a new planetary system after billions of years. These scenarios are highly speculative, but they illustrate how rogue planets might connect otherwise isolated islands of habitability across the galaxy. For now, we have no way to search for life on rogue planets directly, because these worlds are too faint and too distant for detailed observation by current methods. Future technologies might change this. Perhaps gravitational wave detectors could somehow sense the mass distribution of rogue planets, or new imaging techniques could resolve their surfaces directly. Until then, the question of life on rogues remains theoretical, a fascinating possibility that we cannot yet test with empirical observations from our current technological position. What we can say is that the conditions for life might exist on some of these wandering worlds, even in the permanent darkness of interstellar space. The thought of life persisting on a planet that orbits no star, surviving in darkness for billions of years, is both humbling and strangely hopeful to contemplate. It suggests that life, once it arises, might be remarkably resilient, capable of enduring conditions that would seem utterly hostile to us, surface dwellers on Earth. The universe may be more hospitable to life than it first appears, with habitable niches hidden in unexpected places far from any stellar warmth or visible light. Even the cold, dark spaces between stars might not be entirely empty of living things pursuing their quiet existence. In the next part, we will slow down and imagine what it would actually be like to exist on a rogue world, the endless night, the unchanging stars. If you could somehow stand on the surface of a rogue planet, the first thing you might notice is the sky, unchanged, unmoving, eternal. There would be no sunrise coming, no shift from darkness to light, no sense of time passing through daily cycles that we take for granted. The stars would hang fixed in their positions, slowly drifting only over thousands of years as the rogue moved through the galaxy on its long journey. Day and night as concepts would simply not exist. There would only be night stretching backward and forward through time without limit. The darkness would be absolute in a way that is difficult to imagine from Earth, where even the darkest nights have some ambient glow. On a rogue world far from any star, the only light would come from the stars themselves, appearing as distant pinpoints against pure black surroundings. The Milky Way would arc across the sky in stunning clarity, unobscured by any atmospheric haze or light pollution from artificial or stellar sources. Yet no single star would stand out as your star. No sun, no home, just countless distant suns belonging to other worlds. The temperature on the surface of an ancient rocky rogue would be almost impossible to survive, hovering just a few degrees above absolute zero indefinitely. At these temperatures, conventional human technology would fail almost instantly, and no unprotected human could survive for more than moments outside. The frozen atmosphere beneath your feet would not feel like snow or ice. It would be harder than steel, a solid layer of gases like nitrogen and oxygen. Everything about the surface would be utterly still, with no wind, no weather, no sound of any kind to disturb the silence stretching endlessly. Time on a rogue world would flow differently, not because physics changes, but because there would be no markers to measure its passage reliably. On Earth, we divide time by days, seasons, and years, all defined by our relationship to the Sun and our orbit around it naturally. A rogue planet has no such reference points. no periodic cycles to break the uniformity of existence into discrete intervals for measurement. Billions of years could pass on a rogue world, and nothing about the external environment would indicate that any time had passed at all. If you looked up from a rogue planet in the outer galaxy, far from the dense stellar regions near the core, the sky might seem almost empty. Only a few thousand stars might be visible to the naked eye, scattered sparsely across the black expanse in lonely configurations. The galactic center would be a faint, distant glow on one side of the sky, barely perceptible as a slight brightening against the overall darkness. You would feel isolated in a way that has no parallel on Earth, adrift in a vastness that offers no landmarks or reference points whatsoever. Alternatively, if your rogue planet happened to pass through a dense star-forming region, the sky might briefly come alive with spectacular views. Nebulae would glow in soft pinks and blues, illuminated by the young, hot stars embedded within their gas and dust clouds. Pillars of creation might stretch across the darkness like vast cosmic sculptures, visible in ways never possible from worlds orbited by bright stars. For a few million years, brief by cosmic standards, the rogue would drift through this luminous nursery before emerging again into emptiness. The surface beneath your feet would tell its own ancient story, frozen in place for billions of years without change or erosion. On Earth, landscapes are constantly reshaped by wind, water, volcanic activity, and the slow movements of tectonic plates over millions of years. A rogue planet with no internal heat would have none of these processes, preserving its surface features essentially unchanged since formation. Impact craters from ancient collisions would remain pristine, their rims sharp and unweathered by any atmospheric or geological activity whatsoever. If the rogue world retained any internal heat, the surface might occasionally show signs of activity, cracks, vents, or even cryovolcanoes. These features would release material from below, perhaps water ice or nitrogen slush, creating temporary disturbances in the otherwise frozen stillness. But such activity would be rare and localized, separated by millions of years of quiet between episodes of geological expression. The landscape would seem eternal, patient, waiting for nothing in particular as time continued its silent flow forward. Standing on this world, you might look up and try to identify familiar constellations, only to find them utterly unrecognizable from this vantage point. The patterns we see in Earth's night sky depend entirely on our specific location in the galaxy, and a rogue planet could be anywhere. Orion, the Big Dipper, Scorpius, none of these shapes would exist from a rogue world's perspective. Replaced by entirely different random arrangements, the stars would be just as numerous and just as beautiful, but they would belong to a different sky, a foreign night. The sense of solitude on a rogue world would extend beyond physical isolation to something deeper and more philosophical in nature. This planet has never known the warmth of a sun, never been part of a family of worlds circling a common parent star. It has always been alone, or perhaps it was once part of a system and was cast out, abandoned to wander forever afterward. Either origin story carries a certain quiet melancholy, a sense of cosmic loneliness that is difficult to fully articulate in words. Yet there is also something peaceful about imagining such a world, something restful about a place where nothing is expected or demanded. No life needs to evolve, no conditions need to be maintained, no cycles need to repeat. The rogue planet simply is, existing without purpose or destination. It drifts because that is what objects in space do, following the curves of space-time laid down by the galaxy's mass distribution. There is no struggle on a rogue world, no striving, just the quiet continuation of existence through endless time. The The horizon on a rogue planet would be barely visible, a faint line where the starlit ground meets the starlit sky in near darkness. Without a sun to illuminate the landscape, your eyes would adapt to see only by starlight, perceiving shapes as vague shadows at best. Movement would be difficult and slow, each step taken carefully across terrain you could barely see in the dim ambient glow. Yet the stars above would seem impossibly bright by comparison, your dark adapted eyes drinking in their ancient light with unusual sensitivity. If you remained on this surface long enough, impossibly, hypothetically, you might notice the stars slowly shifting their positions over thousands of years. The rogue planet's motion through the galaxy would gradually change which stars appeared in which parts of the sky, like a very slow panorama unfolding. New stars would rise from one horizon, while others set below the opposite edge, taking centuries or millennia to complete their transit. This would be the only clock available, the only measure of time passing, the slow revolution of the galaxy itself. The silence of a rogue world deserves particular attention because it would be more complete than any silence available on Earth today. Even in the quietest places on our planet, there is always some vibration, some distant rumble, some atmospheric movement creating faint sounds detectable. A rogue world with a frozen or absent atmosphere would transmit no sound at all, leaving only the noises you brought with you. Your heartbeat, your breathing, the sounds of your own body would be the only audio in that entire world. In this absolute quiet, thoughts might seem louder, more present, more insistent than they ever do in our normally noisy existence at home. There would be nothing to distract you from your own inner experience, no external stimuli competing for your attention at all. The rogue world would offer a kind of sensory deprivation that might be terrifying or might be profoundly peaceful, depending on your state of mind. Perhaps, in such stillness, something like rest would come more easily than it ever does on our busy, bright, noisy Earth. The night on a rogue world has no end, and in a way, that is both its defining feature and its strange gift to offer. There is no waiting for dawn, no anticipation of change, no cycle of hope and disappointment tied to light and darkness. There is simply the continuous present moment, stretching forward without limit or interruption, asking nothing and promising nothing. And in that endless night, a kind of peace might exist that we can only glimpse in our brief, sun-governed lives. As we prepare to continue our journey, we will next explore the immense timescales over which rogue planets travel through our galaxy. Rogue planets do not remain stationary in space. They move through the galaxy on journeys measured in hundreds of millions of years. Like all objects in the Milky Way, they orbit the galactic center, following curved paths determined by the combined gravitational pull of billions of stars. Our own sun takes about 230 million years to complete one orbit around the galaxy's core, and rogue planets follow similar timescales. These journeys are so long that the galaxy itself changes significantly during a single orbit, with stars forming and dying along the way. The speed of a rogue planet through space is typically quite high by human standards, often tens of kilometers per second relative to nearby stars. At these velocities, a rogue world covers enormous distances over time, crossing light years of space over millions of years of travel continuously. Yet, because the distances between stars are so vast, these speeds feel slow. A rogue planet might take hundreds of thousands of years to pass between neighboring star systems. The journey is marathon rather than sprint, endurance rather than velocity, patience rather than urgency. When a rogue planet is first ejected from its birth system, It may be traveling at exceptional speeds relative to its former home star. Some ejected planets reach velocities of 50 or even 100 kilometers per second, fast enough to eventually escape the galaxy entirely over cosmic time. These hypervelocity rogues will never return, sailing outward into intergalactic space, leaving the Milky Way behind forever after their ejection. They become truly isolated, separated not just from their birth star, but from all stars, drifting between galaxies in the ultimate emptiness. Most rogue planets, however, travel at more modest speeds and remain gravitationally bound to the Milky Way throughout their existence. They settle into orbits around the galactic center, their paths influenced by the mass of everything they pass: stars, nebulae, dark matter halos, and other invisible structures. Over billions of years, their orbits may change gradually as gravitational encounters slowly modify their trajectories through subtle, accumulated effects. The journey is never quite the same twice, even for the same planet completing multiple galactic circuits. The regions a rogue planet passes through during its journey vary enormously in character, density, and activity over galactic scales. Near the galactic center, stars are packed closely together, and the rogue might pass within a few light years of dozens of stars over relatively short periods. In the outer galaxy, stars are sparse, and the rogue might travel for millions of years without coming particularly close to any stellar neighbor. The galaxy is not uniform, and a rogue planet's journey samples this diversity over cosmic time. Some rogue planets will inevitably pass through star-forming regions, where new solar systems are being born from collapsing clouds of gas and dust. These regions are chaotic and energetic, filled with radiation from young stars and shock waves from stellar winds and supernovae explosions. A rogue planet passing through such a region would be bathed in more light than it has experienced in billions of years of wandering. For a brief cosmic moment, perhaps a few million years, it would almost seem to belong to a stellar neighborhood again. Other parts of the journey take rogue planets through voids, regions of the galaxy where stars are exceptionally rare and emptiness dominates completely. These voids are not entirely empty, but they contain far fewer stars per unit volume than average galactic regions typically possess. A rogue planet in such a void would be profoundly isolated, with the nearest star perhaps dozens of light years away in any direction. The sky from such a location would appear unusually dark, with fewer stars visible than from more populated galactic regions. Occasionally, a rogue planet's journey brings it close enough to another star system that gravitational interactions become significant and measurable. These close encounters can alter the rogue's trajectory, speeding it up, slowing it down, or changing its direction of travel entirely. In rare cases, the encounter might be close enough that the rogue planet is captured, settling into orbit around the new star permanently. Such captured rogues would become normal planets again, ending their wandering and joining a new stellar family. The probability of capture is very low, however, because the conditions must be precisely right for a permanent orbital insertion to occur. The rogue planet must approach at just the right speed and angle, and other planets in the system must help absorb excess energy for the capture to succeed. Most close encounters simply deflect the rogue planet without capturing it, sending it on a new trajectory that may or may not bring future encounters. The galaxy is too vast and too empty for captures to be anything but rare exceptions. Over the full age of the universe, nearly 14 billion years, a rogue planet might complete dozens of orbits around the galactic center entirely. During that time, it might pass through hundreds of different galactic environments, sampling the full diversity of the Milky Way's structure and content. It might witness the birth and death of countless stars from a distance, seeing supernovae light up distant space. The rogue planet accumulates experience of the galaxy that no planet bound to a star could ever match. The journey of a rogue planet is perhaps the longest journey that any coherent object can make in the universe naturally. Stars eventually die, galaxies eventually merge, but a cold, inert rogue planet can persist essentially unchanged for trillions of years. As long as it avoids collision or capture, it simply continues, traveling without destination, existing without purpose. There is something hypnotic about contemplating such longevity, such patient persistence through cosmic time. As we continue, we will imagine what the galaxy might look like from the perspective of a rogue world drifting through it across eons. From the perspective of a rogue planet, the galaxy is not a static backdrop, but a slowly shifting panorama that changes over millions of years. Stars that once appeared on one side of the sky gradually migrate to the other, their apparent positions changing as the rogue moves through space. The constellations, if one chose to define them, would dissolve and reform over millennia, never stable, always in slow transition. Nothing is fixed from a rogue world's point of view, nothing except the endless continuation of the journey itself. The Milky Way's spiral arms would be a feature to pass through, rather than a permanent home for any wandering planet. These arms are denser regions of stars and gas, sites of active star formation, brighter and more crowded than the spaces between them. A rogue planet might spend tens of millions of years crossing a spiral arm, bathed in slightly elevated starlight before emerging into quieter regions. Then it would coast through an inter-arm gap where stars are sparser and the darkness deepens once again. If a rogue planet could somehow be aware of its surroundings, it would perceive time very differently than we do on Earth. Our lives are structured around days, seasons, and years, all defined by our relationship to the sun and its reliable cycles. A rogue world has no such structure, no natural units of time imposed by celestial mechanics, only the nearly imperceptible movement of distant stars. Awareness on such a world would need to operate on geological or astronomical timescales to notice anything changing at all. Other rogue planets would occasionally pass by, though such encounters would be extraordinarily rare, given the vastness of space between wandering worlds. Two rogue planets might pass within a light year of each other once in a billion years, briefly becoming each other's nearest neighbors in the dark. Neither would likely be aware of the other, both being inert, frozen, and unobserving, just matter passing matter in the void. Yet something almost poignant exists in imagining these lonely encounters between worlds that share the same cosmic fate. The center of the galaxy, where a supermassive black hole resides, would be a distant glow on the rogue planet's sky for most of its journey. This glow comes not from the black hole itself, but from the dense concentration of stars orbiting near it, their combined light visible across thousands of light years. The rogue planet's orbit probably keeps it far from this central region, out in the safer, calmer suburbs of the galactic disk. The bright heart of the Milky Way remains forever distant, a landmark that never draws closer despite endless traveling. Globular clusters, ancient spherical collections of hundreds of thousands of stars, might occasionally appear as fuzzy spots of light in the rogue's sky. These clusters orbit the galactic center in their own long paths, sometimes passing through the disk where most rogue planets travel on their own journeys. An encounter with a globular cluster would be a rare spectacle, the sky briefly filling with more stars than usual before the cluster recedes again. Such events might occur only a handful of times in a rogue planet's entire multi-billion-year existence. Supernovae would be the most dramatic events visible from a rogue planet, brilliant explosions that outshine entire galaxies for brief weeks or months. From a safe distance of dozens or hundreds of light years, a supernova would appear as a new star in the sky, suddenly present where nothing visible existed before. Over weeks, it would fade, returning the sky to its normal state of quiet, scattered starlight across the darkness. The rogue planet would continue onward, unaffected, having witnessed the death of a star without being touched by its violence. Occasionally, a rogue planet might drift close enough to a planetary system to observe it, if observation were possible for a frozen, lifeless world. It might pass within the outer reaches of another solar system, where comets and icy bodies orbit in distant, slow trajectories around their star. For a few thousand years, it would travel through this outer zone, technically inside another star's gravitational domain, before exiting again into free space. Such passages would be the closest the rogue ever comes to belonging somewhere again. The rogue planet carries no memory of its origin, no record of the star it once orbited or the circumstances of its ejection into the void. If it formed independently, it has no stellar parent to remember at all. Only the cold cloud of gas from which it condensed long ago. Its past is irretrievable, locked in the arrangement of atoms that composed it at formation, invisible to any external observation. The rogue planet simply is what it is now, without history or identity, pure existence without narrative. The future of a rogue planet stretches forward almost without limit, measured in timescales that dwarf all of human history and civilization. Long after our sun has exhausted its fuel and faded to a cold white dwarf, rogue planets will still be drifting through the galaxy, undisturbed. Long after the last stars have burned out, in a dark and quiet cosmos, rogue planets will remain, cold and patient. They are perhaps the most enduring inhabitants of the universe, outlasting almost everything else that exists. As the rogue drifts onward through the endless dark, we might imagine what final thoughts could accompany such eternal wandering, if thoughts were possible. There is nothing urgent about this journey, nothing that needs to be accomplished or achieved or resolved during travel. The rogue planet simply moves, because movement is what remains from its formation and ejection long ago. And in this purposeless continuation, there is something almost restful, almost peaceful, almost like sleep. We will conclude our exploration with some final reflections on these wandering worlds and their quiet place in the cosmos. The rogue planets of our galaxy number in the trillions, perhaps more, each one following its own unique path through the darkness between stars. They represent a hidden population, a shadow galaxy of worlds that emit no light and orbit no sun and pass unseen through the void. For every star you see in the night sky, there may be 20 or more rogue planets drifting invisibly through the same region of space. The universe is far more crowded than it appears, filled with dark objects moving silently through the cosmic emptiness. These worlds challenge our intuitive understanding of what a planet should be, what conditions it should orbit under, what role it should play. We think of planets as companions to stars, lit and warmed by their parent suns, participating in orderly solar system arrangements that orbit predictably. Rogue planets belong to no such order, follow no such rules, owe allegiance to no stellar parent guiding their paths. They are independent, solitary, free in a way that no sunbound planet can ever be. Some rogue worlds were born in chaos, formed in young solar systems only to be ejected by gravitational encounters with sibling planets or passing stars. Others may have formed alone, condensing from gas clouds in the same way stars do, but never gathering enough mass to ignite fusion. Their origins are diverse, their fates are similar. Endless wandering through the galaxy until the universe itself grows old and cold and dark. The details of beginning matter less than the commonality of the long journey ahead. The darkness that envelops a rogue planet is not hostile, not threatening, not unkind. It is simply the natural state of most of the universe around us. We live on a rare, brightly lit world, circling an ordinary star in a galaxy where light is the exception rather than the rule. Most of space is dark, most distances are empty, most existence is quiet, and rogue planets inhabit this majority condition without complaint. They belong to the darkness in a way that we, children of a star, can only imagine. If life exists on rogue planets, and it might, in subsurface oceans warmed by internal heat, it would know nothing of sunlight or seasons or the cycles we consider fundamental. Such life would find energy in chemistry and heat rather than in radiation from a star, building ecosystems around volcanic vents on ocean floors perhaps. It would evolve in permanent darkness, never developing eyes to see light that never arrives, never knowing that other worlds exist bathed in stellar warmth. Rogue planet life, if it exists at all, would be profoundly alien to our experience and expectations. We have only begun to catalogue the rogue planets of our galaxy, and the true number may never be precisely known or enumerated. They are simply too dark, too distant, too numerous to count individually with any current or foreseeable technology available. We detect them in glimpses, brief gravitational signals, faint infrared glows, statistical excesses in microlensing surveys, but most remain invisible and uncounted. The rogue planet population is an estimate, a best guess, a vast unknown surrounding us in every direction. What does it mean for our understanding of the universe that planets without stars may be the majority of all planetary bodies existing? It suggests that our own situation, a planet warmed and lit by a nearby star, orbiting predictably in a stable configuration, is rarer than we might have assumed. It suggests that cosmic loneliness is the norm, and cosmic companionship is the exception throughout the galaxy. It suggests that we are fortunate, perhaps, to live on a world that belongs somewhere, rather than drifting endlessly through the dark. Yet there is no tragedy in a rogue planet's existence, no sadness that requires our sympathy or concern from a human perspective. These worlds do not suffer their isolation, do not long for a star they cannot have, do not regret the ejection that set them wandering. They are simply matter arranged in planetary form, following trajectories through space-time according to the same physics governing everything else. Whatever we project onto them, loneliness, freedom, peace, comes from us, not from them. Perhaps the rogue planets can teach us something about existence without purpose, continuation without destination, being without striving toward a goal. In a universe that will eventually grow cold and dark, where all stars will eventually burn out and all warmth will eventually dissipate, the rogue planets are already adapted. They already exist in conditions that will one day prevail everywhere, already persist in darkness that will one day be universal. In a sense, they are rehearsing the final state of the cosmos, demonstrating that existence continues even without light or heat. As you rest tonight, you might imagine yourself drifting slowly through the galaxy like a rogue planet on its endless journey through time. No destination awaits, no arrival is expected, no clock is ticking down toward any particular moment that you must reach. There is only the quiet continuation of movement, the slow passage through space, the patient accumulation of cosmic time. The stars pass by at unimaginable distances, beautiful but unreachable, companions only in the loosest visual sense. The darkness around you is not empty but full of other rogue worlds, full of faint radiation, full of the gravitational presence of matter you cannot see directly. You are not alone in this darkness, even if no companion draws close enough to notice or to reach. Trillions of other wanderers share this same galactic space with you, each on its own trajectory, each carrying its own history frozen in its composition. The void is a community of sorts, if an unknowing one that never meets or communicates. And perhaps in this final image we can find something restful. The idea that existence does not require purpose, that continuation does not require destination, that peace is possible without achievement. The rogue planets drift on, unconcerned, unaware, undemanding, and they will still be drifting long after the last stars have faded from the universe entirely. There is time enough for everything, time enough for nothing, time enough for rest that stretches forward without end or urgency. Sleep well tonight, knowing that the universe is vast and quiet and filled with worlds moving slowly through the darkness, asking nothing of you. The rogue planets continue their journeys as you begin your rest, and they will still be traveling when you wake again refreshed. Whatever dreams may come, whatever rest you find, the cosmos continues its patient unfolding around you without demanding your attention. And somewhere out there, between the stars, a world without a sun drifts onward through the endless, peaceful night.